Hello dear students, now I am going to discuss Cambridge A2 Chemistry May-June 2023 paper 42. A2 Chemistry, this paper 4, May-June 2023 paper 42. Please subscribe, like and share my channel. Let's move. First, number 1a, group 2 carbonate decompose when heated to form metal oxide and carbon dioxide. Number 1, suggest a mechanism for the decomposition of carbonate ion by adding two curly arrows in figure 1.1. So this carbonate ion goes to carbon dioxide and oxide ion, metal oxide. So you know carbon dioxide, carbon oxygen double bond, carbon oxygen double bond, and oxide ion you know given O -2. Here this bond 2 electron go to this oxygen, so this minus and one lone pair electron to become O2 minus. Then this carbon become positive, so this lone pair electron goes to here, it's form double bond. So this why carbon carbon double bond produce. Carbon carbon double bond is produced. Next, describe the variation in the thermal stability of group 2 carbonate. Explain your answer. Group 2 carbonate, you know, variation increases down the group. I mean thermal stability increases down the group. Down the group thermal stability increases. Now explain. You know down the group cation size increases, cation become larger as shell number increases. So charge density decreases as cation become larger, so charge density decreases. That's why cation polarizing power of cation decreases, so cation polarizes anion less. Cation, as cation charge density decreases, so cation polarizes anion less. That's why thermal stability increases. If polarization more, thermal stability less. If polarization less, thermal stability more. So thermal stability down the group increases. Why? Down the group cation size increases, charge density decreases, so polarization decreases, means cation polarizes the anion less. Cation polarizes anion less. Now definition B1, define lattice energy. You know energy released when 1 mole of a ionic compound is produced from gaseous ion. What is lattice energy? The enthalpy change when 1 mole of ionic compound is produced from its gaseous ions. This is the definition. Now number 2, you see lattice energy of group 2 carbonate become less exothermic down the group, decreases. The lattice energy of group 2 oxide also become less exothermic down the group. Lattice energy of metal carbonate and lattice energy of group 2 oxide, metal oxide, change by different amounts going down the group. Now suggest how the standard enthalpy change of decomposition of reaction for group 2 carbonate changes down the group. Explain your reasoning in terms of relative size of the anions. You have to mention size of the anion and relative changes in the lattice enthalpy down the group. You have to mention two things. One is lattice enthalpy, other is size of the anion. So how the standard enthalpy change of decomposition? Enthalpy change of decomposition become more positive. More positive means less negative. So become less negative down the group. Why? Because oxide ion is smaller than carbonate ion. Oxide ion, oxide ion is smaller than carbonate ion. Oxide ion O-2 is smaller than carbonate ion. So lattice energy of oxide become less exothermic faster. So lattice energy of oxide become less exothermic faster because oxide ion is smaller. So lattice energy of group 2 oxide become less exothermic faster. This is the difference. Now number C, potassium sulfide is used as a food additive. The concentration of sulfide ion can be determined by titration using aqueous acidified manganate 7. First, a 25 centimeter cube solution contains 3.4 gram of impure potassium sulfide. Mass is given. 25 centimeter cube of this solution requires 22.40 centimeter cube 0.0250 mole per dm cube acidified manganate to reach the end point. This is the titration. Manganate concentration and volume is given, so you can calculate mole. Then all the sulfide ions are oxidized. None of the other species in the impure potassium sulfide are oxidized. Only sulfide ion are oxidized. Now the reaction occurs as shown by the two half equation. This reaction are given. This one half equation, two half equation. Now first give the ionic equation for the reaction between sulfide ion and acidified manganate ion. So if you add this equation to half equation, you will get overall this equation. But when you add, electron must be cancelled, and to do electron cancel, every half equation must be equal electron. So here first equation is 2 electron, here 5 electron. That's why if you multiply by first equation 5 and second equation by 2, electron number will be equal. Then electron will be cancelled if you add. Now give the ionic equation for the reaction between sulfide ion and acidified manganate ion. So here 2 times manganate ion, 2 manganate ion, 8 to the 16 hydrogen ion, right hand side 10 hydrogen ion. So left hand side 16 minus 10 hydrogen ion. So left side will be 6 hydrogen ion. Then 5 times sulfide ion, 5 mole sulfide ion. Now right hand side, as 2 is multiplied, 2 manganese 2 ion, 2 manganese 2 ion. Water, now this is 4 to the 8 water, now 5 ones are 5. So 8 minus 5, right hand side 3 mole water. Then sulfide ion 1 times 5 sulfate ion. This is the ionic equation for the reaction between sulfate ion and acidified manganate ion. Now calculate the percentage purity of sample of potassium sulfite. You have to show your working, and you see first moles of manganate ion. You see concentration is given, volume is given. So volume centimeter cube divided by 1000, you will convert into dm cube. First of all, moles of manganate ion concentration into volume, you get this mole of manganate ion. This mole you get. Then moles of sulfite ion ratio, moles of sulfite ion in 25 centimeter cube, 5 by 2. This ratio 5 by 2. 5 over 2 times manganate. So you get 1.4 times 10 to the power minus 3. This is in 25 centimeter cube, but this solution is 250 centimeter cube. You see in question, (250 centimeter cube solution, but you calculate for 25 centimeter cube. 250 is the 10 times of 25. Now you see, so moles of sulfite ion in 25 centimeter cube, this moles of sulfite ion in 250 centimeter cube, 10 times more. So 1.4 10 to the power minus 2 mole. Then mass of potassium sulfite, number of mole into molar mass of potassium sulfite, so 2.2162 gram. This is actual mass. Now percentage purity, experimental mass or actual mass divided by calculated mass, 3.40 is given. Here 3.40 gram is given. So now percentage purity, experimental mass divided by calculated mass into 100, 65.2 or 65.3%, you will get answer if you calculate. Now the potassium disulfide is another food additive. The disulfide ion has the displayed formula in the following figure. This is the displayed formula. Deduce the geometry means shape around the sulfur, here alpha sulfur. So you see how many bond present, 1 2 3 4. Around sulfur atom there are 4 bond. 4 bond means geometry or shape will be tetrahedral, and you know double bond in shape, double bond behave as a single electron pair. So total 1 2 3 4 pair of electrons surrounding the sulfur atom. So this shape will be tetrahedral. Next, number 2, state 2 typical chemical properties of transition element. You know, they form colored compounds, they form complex ion, or you can write they behave as catalyst, they show variable oxidation state. Now B, aqueous solution of cobalt 2 salt contains complex ion hexa means 6 hexa aqua cobalt 2. Define the complex ion. You know, complex ion, metal ion is surrounded by ligands. This is known as complex ion. This is a complex ion. Metal ion, cobalt ion is surrounded by water ligands. So define a complex ion. Metal ion is surrounded by ligands. Now is 2 samples of cobalt complexes are reacted separately with an excess of aqueous ammonia, with an excess of concentrated hydrochloric acid, with an excess of aqueous sodium hydroxide. In this diagram, cobalt complexes, excess sodium hydroxide C, excess aqueous ammonia A, excess concentrated sulfuric acid, hydrochloric acid B is produced. Complete the table. You will complete the table. You see, first reagent added to cobalt complexes, formula of the cobalt species form, then color and state the cobalt species form, type of reaction. Now you see, first A, an excess of ammonia, water ligand is 6 water ligand will be substituted by 6 ammonia ligand. So A product will be hexaamine cobalt 2. 6 water ligand will replace by 6 ammonia ligand. So this name will be hexaamine cobalt 2. Now color will be brown solution, or you can write cobalt is a brown, yellow brown solution. This is ligand substitution reaction or ligand exchange reaction. Now you see B, cobalt 2 complexes, aqua complexes reacts with when concentrated hydrochloric acid, and you know this octahedral geometry, but when it reacts with concentrated hydrochloric acid, tetrahedral geometry will be formed. So the product will be tetrachlorocobalt 2, and this is blue solution. This common reaction when if hexaqua cobalt 2 ion, if you add concentrated hydrochloric acid, tetrachlorocobalt 2 ion is formed, and this is color is blue solution, and this also ligand substitution reaction or ligand exchange reaction. Now you see, if aqua cobalt complexes, if you add excess sodium hydroxide, first will form cobalt 2 hydroxide, or you can write cobalt 2 hydroxide tetra aqua. If you write COS whole 2, you get marks, but actual this is the formula, tetra aqua dihydroxy cobalt 2, cobalt 2 hydroxide. This is, you know, precipitate. This is blue precipitate, or you can write pink precipitate. This is reaction type of the reaction will be is precipitation. As precipitate is formed, so reaction type is precipitation reaction. Now see, ethane dioate ion C2O4 negative 2 can act as a bidentate ligand. Number 1, explain what is meant by a bidentate ligand. Bi means 2. A species that donates two lone pairs of electrons to form two dative bond to a metal ion. I mean, bidentate ligand is 1, which donates two pair of electrons to the metal ion to form two dative covalent bond. Then here complete the three-dimensional diagram of this. Show four stereoisomers of two ligand water, one ligand oxalate ion, one bromide, one chlorine. This is oxalate ion. C2O4 negative 2 ligand is representing by this. So total 2, 2, 4, 1, 1, 6. Total coordination number 6. So you can complete this diagram. Here is given already. So two water ligand opposite, one chlorine, one bromine, and now two water same side cis, this trans, one chlorine, one bromine. Then you can draw one water here, another water here, chlorine this isomer, and here also one water this place, another water, chlorine here, this chlorine here, bromine go there. So by arranging different ligand you can shows this four diagram. Now then you are asking state the oxidation state of cobalt in these complexes and type of stereoisomerism shown. So oxidation state of cobalt +3, why +3? You see oxalate -1, this -1, chloride -1, -1, total -4, two oxalate, -4, okay, -4 and -1 here left, so total -3. That means cobalt is +3, metal is total ligand -3, so cobalt will be +3. Here cobalt +3, and type of stereoisomerism will be cis trans, you can write, or geometrical, or you can write optical. You get marks. Let's move. Okay, now number 3, complete table 3.1 by placing one tick mark in each row to indicate the sign of every type of energy change under standard conditions. Energy change always positive, always negative, can be either negative or positive. Now you see bond energy always positive, so here tick mark. Enthalpy change of atomization always positive, energy is needed, so this positive. And enthalpy of formation always, it can be mostly negative but sometimes it can be positive, so enthalpy of formation can be either negative or positive here. Then define standard enthalpy change of atomization. You know, it is the enthalpy change when 1 mole of gaseous atom is produced from its elements under standard condition. And enthalpy change when 1 mole of gaseous atom is produced from its elements under standard conditions. Say 1 mole of sodium standard state solid it's from 1 mole of sodium gaseous atom. This is known as enthalpy, standard enthalpy change of atomization. It is the enthalpy change when 1 mole of, it's not positive, gaseous atom, enthalpy change when 1 mole of gaseous atom, 1 mole of gaseous atom is produced from its element sodium under standard conditions. Sodium standard state solid, so under standard conditions 1 atm pressure and 298 Kelvin temperature, and sodium is standard state solid. Now number C, here table 3.2, yes, there are some values are given. Standard enthalpy change of atomization of silver: first ionization, second ionization, bond energy, oxygen double bond, single bond, first electron affinity, second electron affinity of oxygen, first ionization energy of oxygen, and standard enthalpy change of formation of silver oxide. These values are given. So now you are asking, calculate the lattice enthalpy of silver oxide using the above data. It may be helpful to draw level cycle draw. You may draw or may not draw, no problem, but you have to show your working. You will show your calculation. You know, enthalpy of formation equal atomization, ionization, electron affinity, and lattice enthalpy. If you add, then you get the only lattice enthalpy value is not given, so if you put other values, you will get lattice enthalpies values. Okay, now you see, first you see silver oxide will form 2Ag, then 2Ag will form 2Ag ionization, oxygen double bond break, one oxygen atom will be formed, then oxygen gains one electron, first electron affinity of oxygen, oxygen minus 2n, oxygen forms second electron affinity. So first enthalpy of formation values is given minus 31 equal 2 into 285, because silver oxide Ag2O, so here 2 silver atom will be formed. So at atomization of silver is 285, so 2 times 285, you see atomization of silver 285, so 2 silver atom, that's why times 2. Now you see, then 2 into 2 times 731, 731 is the first ionization of silver, so 2 silver ion is formed, that's why 2 into 2 times 731. Then minus 141 is the, you see, first electron affinity of oxygen, and 798 is the second electron affinity of oxygen plus lattice enthalpy. Then 496, you see 496 is the bond energy of oxygen double bond. So when it form only one oxygen atom, this divided by 2. if you put values, you will get lattice enthalpy of silver oxide minus 2968 kilojoule per mole. This is the answer. Then you see D suggests the trend in magnitude of the lattice energies to the silver compound, silver sulfide, silver oxide and silver selenium. And you see least exothermic, least value silver selenium, then most silver oxide, because oxide ion is smaller, sulfide ion is larger than oxide ion, and selenium ion is most larger, selenium. So down the groups, charge density of anion decreases. Why? Because anion become larger. All are minus negative 2, but oxygen to sulfur ion is larger, sulfur to selenium ion is larger. So their charge density of anion decreases. That's why lattice enthalpy is decreases, and silver oxide is lattice enthalpy more exothermic, and silver selenium is least exothermic, and silver sulfide is medium value. Then E, silver sulfide is sparingly soluble in water. Number 1, give an expression for the solubility product of silver sulfide. You know, silver sulfide when ionizes 2 silver ion and 1 sulfide ion is formed. If it is X, so it will be X and this will be 2X twice. So solubility of X, solubility product KSP silver ion square, because 2 silver and sulfide ion, concentration of silver ion, concentration of sulfide ion, and number of mole goes to power, here 2 power. Then calculate the equilibrium concentration of silver ion in a saturated solution of silver sulfide at 298 Kelvin temperature. Solubility product of silver sulfide is given. So now 4x cube equal this value 1.5 10 to the minus 14. 4x cube how? If you keep here 2x, so 2x square times if x, so 4x square into x, I mean 4x cube equals, so 4x cube equal 1.50 10 to the power minus 14. So if you solve it, you get x value this. So silver ion will be 2 times double, 2x is produced. So concentration of silver ion this times 2, 3.11 10 to the power minus 5 mole per dm cube. Then F, the standard enthalpy change of solution of silver nitrate in water is plus 22.6 kilojoule per mole. Suggest how the feasibility of dissolving silver nitrate in water changes with temperature. Solubility. Feasibility increases as temperature increases. Feasibility increases as temperature increases, because as T values increases, T times del S become more negative. If product of minus T T del S become more negative, so Gibbs free energy become negative. That means solubility of increases because del Z Gibbs free energy equal enthalpy change minus T del S. As temperature increases, so Gibbs free energy decreases. Gibbs free energy become negative. If Gibbs free energy become negative, solubility increases. Next, number 4. A. In aqueous solution, iron 3 ions react with iodide ion as shown. Iron 3 ion reduce and iodide ion is oxidized, redox reaction. A series of experiment is carried out using different concentration of iron 3 ion and iodide ion as shown. This is the table 4.1. Iron 3 ion concentration, iodide ion concentration, and their initial rate is given. So you are asking A. Explain what is meant by overall order of reaction. You know, the sum of the powers to which a concentration of a reactant is raised in the rate law. The sum of powers of concentration of reactant in the rate equation is known as overall order of the reaction. The sum of the powers of concentration of reactant in the rate equation are known as overall order of reaction. Next, you see to use the data in the table 4.1 to deduce the order of reaction with respect to iron 3 ion and with respect to iodide ion. Explain your reasoning. So you have to find out what's the order for iron 3 ion and what's the order of iodide ion. Now you see from experiment 1 or 2, if when concentration of iron 3 ion 3 times, keeping iodide ion constant, rate become 3 times. This times 3, you will get this value. So concentration is directly proportional to the rate, so reaction is first order. From experiment 1 or 2, when concentration of iron times 3, rate becomes 3, directly proportional. So the reaction is first order with respect to iron 3 ion. So reaction is first order with respect to iron 3 ion. Now from experiment 1 and 3, 1, 2, 3, when iron concentration is double, rate become double. As for iron 3 ion is order is 1 and concentration of iodide ion double, rate should be 2 times for first order, but rate increases 8 times. So when iron concentration double, iodide ion double, rate increases 4 times. That means when iodide ion double, rate increases 4 times for iodide ion. So the reaction is second order with respect to iodide ion. Okay. From experiment 1 or 2, if concentration of iron 3 ion double, rate become double. So the reaction is first order with respect to iron 3 ion. And from experiment 1 to 3, if concentration of iron 3 ion double and concentration of iodide ion double, so rate become 2 times, and for this 4 times, total rate increases 8 times. So the reaction is second order with respect to iodide ion. Then number 3, use your answer 2a2 to construct the rate equation for this reaction. So rate equal K means rate constant, concentration of iron 3 ion, this one order, and concentration of iodide ion second order. So 4, use your answer to A3 and the data from experiment 1 to calculate the rate constant K for this reaction. Include the units of K for experiment 1. So K equal rate is given, concentration of iron 2 is given from experiment 1 0.4, and concentration of iodide ion 0.02 square. So you get 16.5 and mole inverse to dm cube per second. How? This is mole per dm cube per second, and this is mole per dm cube, and this is mole per dm cube square. So then remaining mole inverse to dm6 per second, you will get unit. Then 5, describe the qualitatively the effect of an increase in the temperature on the rate constant and on the rate of reaction. And you know, if you increase temperature, rate of reaction increases. So as rate reaction increases, so rate, this is the rate, as rate increases, so rate constant also increases. That means temperature increases both rate and rate constant. Next, in aqueous solution, iodide ion react with acidified hydrogen peroxide as shown. Iodide ion reacts with hydrogen peroxide acidic medium to produce iodine and water. The initial rate of reaction is found to be first order with respect to iodide ion and first order with respect to hydrogen peroxide and zero order with respect to hydrogen ion. So first order iodide ion and first order hydrogen peroxide ion. Now there are 4 steps: step 1, step 2, step 3, step 4. Now you are asking 1, suggest which of the steps 1, 2, 3 or 4 in this mechanism is the rate determining step. And you know, rate determining step involve hydrogen peroxide first order, iodine first order. So this is order 1. So step 1 will be the rate determining step 1, because this has 1 mole of H2O2, because for H2O2 order is 1, and 1 mole of iodide ion, because this given first order with respect to iodide ion and first order with respect to hydrogen peroxide. So step 1 is the rate determining step, because 1 mole of H2O2 and 1 mole of I minus involved in this step. Then one, suggest which of the steps 1, 2, 3 or 4 in the mechanism is the rate determining step 1. Okay, I told. Now number 2, identify a step in figure 4.1 that involves a redox reaction. And you say step 1, because iodide ion oxidize, iodide ion oxidized from -1 to 0, and oxygen is reduced from -1 to -2. So this is a redox reaction. In step 1 you see here iodide ion -1, here iodide ion +1. Iodide ion, step 1 you see iodide ion -1 to here +1. So iodide ion is oxidized and oxygen is -1 here. Hydrogen peroxide, oxidation number oxygen is -1, and here water, oxygen is -2. So iodide ion is oxidized, oxygen is reduced, that's why it is a redox reaction. So step 1 is the redox reaction, because iodide ion oxidized from -1 to 0 and oxygen is reduced from -1 to -2. Or you can write also step 3, because step 3 you see iodide ion -1 to 0 oxidized, and HiO, iodine is +1, here 0. So HiO is reduced and iodide ion is oxidized. Step 3 also you can tell it is a redox reaction. Now next one, number 3, suggest the role of HiO in this mechanism, explaining your answer. Intermediate, hydroiodic acid HiO role is intermediate. Why? It is produced in step 2 and again used up in step 3. So it is formed as intermediate. You see step 2 HiO is produced and step 3 HiO again used up. That means a role of HiO is as intermediate. Also you can write role of SiO, also you can write works as a oxidizing agent, as it oxidizes iodide ion to iodine. So you can write it works, role of it is intermediate or role is oxidizing agent. Anyone you can write, you get marks. Okay, thank you dear students.